Okay, here's one more example for class 14 and in statics, and this is a 3D shaft, another 3D shaft problem, a little bit more complicated this time. That's good, we can handle it, no big deal. So what we're told here is that there are two pulleys. We're given both of the forces, both of the tensions. You'll notice that this one's larger than that. And then we're given one of the tensions here, but we have a missing one here. And once again, I don't like, I think, what did I call this? B2. That's what I said, a B2, FB2, because it's located at B. They already gave us one of them, so I'll call the other one B2. To be or not to be? B2. And okay, so the both pulleys are fixed in the shaft in terms of the constant angular velocity. That's good. That means that it's in equilibrium. It's not accelerating. So the net moments that are being created by this and this, they should be equal to each other and cancel each other out. If there was an off balance, that it would cause the thing to accelerate. Just determine the horizontal tension of that guy, of the belt, and find the components in the reaction that are happening at this bearings C and D. And they tell us that this is 45 degrees right here. So one of the first things we want to do is do the FBD that's down the length, and I think I'm going to go ahead and I'm going to use their directions as part of this, but even though I kind of prefer, I'm going to go ahead and use these views. That's what I'm saying. All right, so we're going to look at the YZ plane right here. So it looks like this, YZ. I like Y being upwards. It just bothers me. So we're going to look at it from this direction right here. And so I'd see the big one is in the background and the small one's in the foreground. And we have like little bearings, and we're just going to stick in a couple of reactions right there as placeholders, because the reactions are different between C and D, but they are on top of each other. You can't tell them apart. Here we're going to have these forces coming down, so 65 newtons and 80 newtons. And then coming this way right here, that's our unknown, FB2, and then coming upwards at 45 right there, we're told that that's 50. Now later on it's going to be easier for us to actually break this into components. So I might do that right away, and this is going to be 50, and I'm actually not putting them on the free body diagram. This is information that I'm going to need later on right here, because I don't want to think that they're forces that we also have to include right here. This is the force that we have to deal with, period. But here is what the components are, because it would be useful to us. And this is the cosine of 45, and this right here is 50 times the sine of 45, and of course sine of 45. Cosine of 45 are the same thing, but that ends up being 31.82 newtons. That's something I'm going to want to know in a minute. But let's just, right here, I think we have everything we need. We also know that, by the way, the radius of this is 80 millimeters and the radius of this is 50 millimeters. And we can go ahead and use millimeters. A lot of times I'll change to meters, but they're all going to cancel out anyway, so it's fine. So we take the sum of the moments about the x-axis, right, that's coming out of the plane, equal to 0. And so we take, I'm just going to go systematically, 65 times its radius, and it's clockwise, 65, and the radius is 80. And let's go minus 80, because that's that force, times the moment arm, which is the radius right here, right? That's the perpendicular distance right there. So 80 times 80. By the way, that right there combined, that would give us what the net torque is going to be because of this pulley. The other pulley better have the same torque, because those torques need to balance out, right? And now, so we come into this guy. He is going clockwise, so negative 50, and his distance right there is that radius is also 150. Well, not also 150, but it happens to be 150. This guy, he is also 150, so that's where the word also came from. And he's going counterclockwise, so he's the FB2 times our 150, and it has to be equal to 0. And so the FB2, the unknown, turns out to be 58 newtons, right? So this one is larger than this one, but that kind of makes sense. This one tends to make it want to go, if we're looking down here, this one makes it want to go clockwise. So this one right here better balance out by being larger than this and wanting to make it go counterclockwise. They need to balance out. Otherwise, things going to accelerate. So the moment's torque has to balance out between these two pulleys. So now we have that unknown. That's good. And now, and by the way, the torque that's placed on this thing would be like 80 minus 65 times 80, and that turns out to be like 120 Newton millimeters, right? Because we're using millimeters here. So what is the torque? The torque is 120 Newton millimeters, which is a weird thing. Most time we go Newton meters, so 0.12 Newton meters. All right, so the next FBD I'm going to decide to do is I'm going to go the ZX plane. So I go X that direction, Z that direction. So I'm at like creepy eye. It's looking from that direction onto the thing. So I make a light sketch for the shaft. I draw this pulley, and I draw this pulley. Right? Oop. I'm still here. You scared the hell out of me. So, but I don't need to be here anymore because office hours are off. So I'll leave the session. Boy, that thing's loud. Damn. Turn that down. Turn that stuff down. Turn it down. Is that Freedom Rock? Turn it up. All right. So what's happening on here is you're going to see both of these forces. So it's going to be 65 plus 80. And that turns out to be 145. All right, so there's a total of 145 downwards onto here. And for this one, we are only going to see the upwards component of this 50 newtons. So it's really this 50 times the sine of 45, which we happen to know is 31. 31.82. And then you take a look at the reactions, and I think we're going to have a reaction upwards here. And I think it's going to be upwards right there. You can't quite be sure. If this was large enough, it might need to have a downwards reaction. I think of that as being the teeter-totter kind of situation. And so this is C in Y direction, so I'm going to go R, C, Y, racy. And this one's going to be D, so it would be ready. Are you ready? And the distances are 300, 250, and 200. We're ready to go. And we'll take the summation of moments. Let's take it about C. And if we were going to be very specific, that's going to be C, Y. All right, because it's Y is coming at us, so it's like we're going here and going in a counterclockwise direction. So we see we have negative 145. Moment arm is 300. And then we have a positive 31.82, and it's going to be 300 plus 250 or 550. And then we have, this is also positive, this R dy, and we add another 200, so that's 750 equal to 0. And we find that our R dy is 34.67 newtons. And by the way, we got a positive answer, so we did choose correctly here. And we want to find what the other guy is, so we take the sum of the forces in the Z direction, which happens to be that a ways in this view. And we say RCY, so racy, minus 145, and then plus our 31.82, and then plus our 34.67 equals 0, and we get a racy reaction as 78.51 newtons upwards. That's in one plane. Now we need to look down at the thing. Creepy eye, looking down. And I think I want to go the XY, right? So we did the YZ, we did the XZ, now we need to do the YX, or XY. But the way that they have the thing written out, and the best way to go along here, I think, is to make it like this right here, YX, like that, because it's easiest the way that they have this picture arranged to put the thing there. And so actually the view looks the same, it's just the forces that are on there differently. And let's see. So we don't see any forces in this direction on this, right? Because we're looking down at this and all those forces are in the Z direction, which is into the plane, into the paper here. Here we're going to see things going to go downwards, but it's not only this guy, but it's a portion of this, right? So it's this direction plus that portion right there. So it's going to be this FB2 plus that 31.82, right? So I might even write that down somewhere. I'm going to go 58 plus 31.82, and I wrote that down as 89.82 newtons. That's just like a little aside that I told to myself. So this is my 89.82 newtons. And so the reactions have to be both this direction right there, right? They have to support that. So we have RC. Oh, you know what? I really messed up down here. I called this guy Y, didn't I? I hope that didn't confuse you, and I don't want to go back and record this whole thing, so I apologize if I made that crazy mistake. I got so excited about pronouncing the thing. I called it ready. It could be reds. And this is Rizzi. I don't know how to pronounce that. How would you pronounce that? You wouldn't, because I'm weird. People don't do that. Right? All right, there you go. Sorry about that. He's racy. He's ready. Jump the gun. And here's 300, and here is 250, and here's 200, and now we're ready to go with the sum of the moments about C, and now it's about the Z-axis that we're doing the thing for, right? And we'll pick as the page. Is that correct? Yeah, that's still, yeah, actually that is right-hand rule. Is still, we're still okay with that. All right. And let me see, I'm going to go negative 89.82. This moment arm is going to be 550. Reactions, positive, ready, and times 750. So the ready is 65.87, according to what I wrote down previously. And then we take the sum of the forces in the y direction, and that is downwards in the way that we're drawn here. So we have a negative RCY and a negative, nope, positive, oh, I can just make it positive, positive 89.82. And then we're going to have a negative 65.87. So we get a racy of 23.95 newtons. That ways, right? So it's good to reflect on what directions these things are going to end up coming up right here. But you can see that if we were at D right here, so at D, and we're looking in the YZ direction right here, that we would definitely be at D. We'd be going upwards right here, right, of like 65.9 newtons, and then in the Z direction we'd be going into the Y direction. We're going into the negative Y direction, right? Because this is going here, right here. So that would be coming it this way right here. So that would be the way that it would look. Did I do this wrong? Yes, I did do that wrong. Why even bring it up if you're going to do it wrong each time? So this is going to be the 34.67, 34.7 newtons, and then this is going to be the RDY 65. Yeah, this is 65.9 newtons. And the same idea for this one right here. For at C, right? If we're taking a look at this bearing and trying to think what kind of force are the bearings placing onto the shaft itself, as opposed to the shaft being putting onto the bearings. And the CY is that direction of the 20 is actually 24 newtons, and CZ is going upwards of 78.5. So like that way up there and that way right there is what the bearings place on the shaft, and of course the shaft does the opposite to the bearings. So those are our procedures when we want to break the thing into 3 views. I think this is much more informative than trying to take the cross products and that kind of thing. But the cross products are correct. That is the way to do things and to solve things, but this is the way I prefer to do it. I'm not even sure where I learned to do it this way, but this is the book doesn't show it this way, but I might ask you to do it this way. Thank you.